Aha, we've learned something. What about this one? I'm cycling at fairly constant speed, but my velocity is a vector, so it has magnitude and direction. My velocity keeps changing. I'm travelling south, west, north, then east. We'll leave circular motion until next week, but remember that because my velocity is changing, I am accelerating even though my speed is constant. Any change in velocity is an acceleration. For now, we'll look at motion in a straight line. 400 years ago, the Italian physicist Galileo Galilei founded the science of mechanics with very simple equipment, such as you might use in home experiments. Here's an example. Measure x along the board with 0 here and t from when the ball is released. We can see it's getting faster. Both displacement and velocity are increasing. We can plot the x displacement from 0, the x-coordinate, as a function of time t. Here we're plotting the position of the centre of the ball. With macroscopic objects, we need to choose a representative position. What point on this object would we choose? We shall neglect internal motion and will give an object's position as just a point in space. Technically, this means we are treating them as particles. Now, back to our rolling ball. Here's displacement versus time. Over this time interval, the average velocity is just the displacement divided by the time taken. Here, x over t, which is 1.14 metres over 4.2 seconds, which is 0.27 metres per second in the positive x direction. Here we can also estimate the time at which the ball had a velocity equal to the average velocity. Looks to be about 2.1 seconds. We can measure average velocities over smaller time intervals too. We use the Greek letter delta to mean the change in. Write this a few times so you get used to it. Delta x is the change in x. So the average velocity over this small time interval delta t is delta x over delta t. Here's a plot of the average velocity measured over single frames. Well, there are substantial error bars because of experimental uncertainties. It doesn't move very far in one frame, so the proportional error in velocity is large. It's possible to measure things much more precisely, of course, with different technologies. But uncertainties in measurement are always present, so we can never know precisely what the so-called instantaneous velocity is at any given time. We can, however, fit smooth curves to the data, but remember that those curves are only theoretical approximations. Here's a simpler case. The air track is level and the speed and velocity are both very nearly constant. With this gadget, the cushion of air prevents contact and removes friction. Using the scale for distance and camera frames to measure time, we plot x versus t. Question for you. What is the magnitude of the average velocity between t equals 0 and t equals 1.6 seconds?